Hello everyone, my name is Jerome Gaysse. I am Senior Technology Analyst at Silinnov Consulting, focusing on the data center carbon footprint reduction thanks to the use of emerging storage and computing technologies. It is a great pleasure for me to be a keynote speaker for the Storage Developer Conference EMEA 2022. That's a great opportunity to highlight a new kind of design criteria. In addition to traditional criteria like the performance, TCO, security, or scalability, let's add the environmental impact criteria, and especially the carbon footprint, which is responsible of the climate change. You, as a storage developer, you must take it into account and work on an eco-design roadmap. So, in this presentation, I will start with a few definitions about the carbon footprint. Then, I will introduce a tool which is able to calculate the carbon footprint of a system with different levels. And let's see how it can be applied to a computational storage benchmark and how it can be used for eco-design systems. The environmental impacts of the data center markets are huge. A lot of water is used for the cooling and the manufacturing of the equipment. There are tons of servers to recycle. The server market represents more than 10 million units per year. Many materials are necessary to produce the chips, and greenhouse gases are emitted by both the usage and the manufacturing of the data center equipment. This is not viable for a long term, and major changes need to be done on technologies with innovation and eco-friendly features, on system architectures with more efficient data movement, for example, as we will see in this presentation, at the application level as well, with an optimized source code, and on the usage, which is the digital sobriety, and many other ways. In addition, as the environmental impact evaluation is quite new, multi-criteria databases and tools are required in order to measure, calculate, and simulate the system environmental impact. This is a huge and complex work. So, let's focus here in this presentation on the carbon footprint only and how it can be reduced thanks to computational storage. Computational storage. So you know it very well, but just as a quick reminder, the main concept is to move computing resources closer to the storage. So as a result, you really reduce the data movement. For example, a computational storage drive, or CSD, will process the data directly in the SSD controller, avoiding to move data from the SSD to the host RAM and CPU. The host CPU becomes just a system orchestrator. On the picture here, the main processing part is the green one, which is part of the SSD controller. That leads to multiple benefits, where the two most important ones are better performance and a lower power consumption. A better performance because you save time in the word processing task. The SSD controller processes directly the data from the NAND flash. a lower power consumption, because moving data is not energy free. Moving data may represent a huge percentage of the total energy in a standard system. Regarding the lower power consumption, there are multiple direct benefits behind. The first one, which is obvious, is that you reduce the energy bill at the end of the month, which can be very high for data center suppliers. Another consequence is that you require a smaller electricity infrastructure. Then, a lower capex for data center or less space, which is critical for embedded systems, such as industrial and transportation applications. Regarding the environmental impact, taking into account just this lower power consumption is not enough to get the full picture. Of course, it is very important, and we understand why, but a more global analysis is more relevant. I mean, a full system lifecycle assessment. The carbon footprint, what is it? You know this word, you heard about it, with the ambitious but mandatory target to become carbon neutral in order to reduce the climate change. The carbon footprint is an estimation of the greenhouse gas emission for a given system during its full life cycle, from the manufacturing to the recycling. The International Greenhouse Gas Protocol splitted the carbon footprint in different categories, which are called Scope 1, Scope 2, and Scope 3. The Scope 1 corresponds to the direct emissions. For example, carbon dioxide emitted by a thermal engine. The Scope 2 is related to the indirect energy power consumption, such as the electricity usage. And the Scope 3 is also an indirect emission, but covering all the other phases where greenhouse gases are emitted. As a result, the carbon footprint is given as a number in ton or kilogram of carbon dioxide equivalent. Why equivalent? Because in fact, the carbon dioxide is not the only greenhouse gas. Other gases are also emitted with different greenhouse gas impact. So in order to ease the calculation and the communication, all the other cases are converted to an equivalency of carbon dioxide. More details on the Scope 1. This part may be quite small if we consider the IT infrastructure only. I mean the server, storage, network, and the hosting data centers, where here the Scope 1 part will come from the diesel generator used as standby power, or from the refrigerant gas of the cooling system. On the other hand, if you consider all the people required to manage this infrastructure, and you take into account the travel trip and commuting, then the Scope 1 part may be quite high. It is quite easy to measure and calculate the Scope 2. This is basically the formula on this slide, which is the multiplication of the power usage by the PUE and the emission factor. The power usage is just the power consumption of the infrastructure itself, measured in watt. The PUE, or power usage efficiency, is the efficiency of the data center building, including the energy used for the inverters and cooling system, so all the data centers facilities. The average is about 1.5. Good data centers come with a value of 1.2 or even lower, with liquid cooling, a very promising technology for data center cooling. And the emission factor is related to the energy mix. It is provided in kilograms of carbon dioxide equivalent per kilowatt hour. The values are very different if the electricity comes from solar, wind, nuclear, or coal. On top of that, data center suppliers can provide electricity with two different approaches: location or market-based, where they can buy renewable energy very far from the data center. The scope 3 is the most difficult part to estimate. It is mainly linked to the manufacturing, transportation, and recycling steps. The manufacturing part is the most important one due to the high level of energy required by the semiconductor industry for the chip manufacturing process. That includes the material extraction, the manufacturing of the silicon crystal used for the wafers, the chip manufacturing with hundreds of phases from lithography to assembly, and product transportation is also considered between all these phases until the servers are installed in the data center. And finally, the recycling, where the systems are disassembled. So, after this introduction on the carbon footprint with few definitions, let's go to the question how to calculate it in the real life. For that, we need data sources and tools. But the real first question is which perimeter to select. As explained in the previous slide, and especially for the scope 1, depending on the perimeter you select, the result will be very different. By the way, let's take what you think relevant for the system you want to analyze. But for sure, let's take the same perimeter if you compare different technology solutions or if you do another analysis 1 year later to measure the evolution. Then you need tools to measure the power consumption and get data to calculate the scope 2, so the PUE and the emission factor that must be provided by your data center supplier. For the scope 3, two possibilities. First, if by chance your product supplier provides a carbon footprint datasheet, then that's okay. Just reuse it. But if not, which is the case most of the time, then let's estimate it through a standard database or with a more detailed model. In any case, another parameter needs to be defined with the scope 3. This is the product lifetime. The products in IT are used for services, and these related services come with an annual average carbon footprint. So for that, you add the scope 1, the scope 2, and you take the scope 3 divided by the product lifetime. So once you have your input data, let's use a tool that will calculate the overall carbon footprint. On top of that, it's interesting to get a detailed analysis. Knowing that the carbon footprint of an infrastructure is 10 tons of carbon dioxide equivalent per year, that's good. But knowing what is the percentage for the CPU, the RAM, the disk is even better, so you are able to optimize and tune your design. Carbon Calculator Studio, a new generation of tools very useful to eco-design systems. The goal is to estimate the power consumption and the carbon footprint scope 2 and 3 of a system. For the power consumption, it is based on a dynamic and static power model. The use of the system configuration and the workload converted in the usage of the different resources, such as the CPU cores, the PCIe interfaces, and the memory channels. For the carbon footprint, so the scope 2 calculation is based on the power consumption calculation and the parameters, such as the PUE and the emission factor. And for the scope 3, it is based on an open source model provided by the Boa Vista think tank. As a result, all the main information are displayed on this dashboard. Obviously, you see the power consumption and the total carbon footprint of the system. We can also have a lower level analysis with the power consumption and the carbon footprint for each subsystem. I used this tool to estimate the carbon footprint benefit of a computational storage technology. The analysis was done on a real benchmark where the company NGD System, a computational storage leader, provided me with the technical specification and the benchmark results. The application is a database running in a virtualized environment. The existing system is a standard architecture with CPU, RAM, and HDD for the storage. The NGD System-based system keeps the same CPU and RAM configuration, but it is fitted with computational storage drives instead of the HDD. We used 1.3 for the PUE, which is quite good, and the average value of the USA for the emission factor. Note that both PUE and emission factors can be optimized, especially with hyperscale data center suppliers using renewable energy. As you can see, our first benefit is that it requires 2 servers only with the CSD, compared to 16 servers with the HDD for the same overall application performance. In terms of power consumption, it is divided by 10, from 8 kW to 0.8 kW. But the carbon footprint is divided by 3.7. This is explained by a 10x factor as well for the scope 2, but a higher value for the scope 3. In fact, in the Carbon Calculator Studio model, the scope 3 data for the non-flash is quite huge compared to HDD, because it requires more energy to produce non-flash compared to HDD. I had the chance to present more analysis details at the past Persistent Memory and Computational Storage Summit, hosted by SNIA as well a few weeks ago. So, as a quick summary, this tool is very useful to evaluate the carbon footprint at the system level, as well as the subsystem level. But the real value of this tool is at another level, the sub-chip level. Why going like this? Even if we get the data for the subsystem, like the CPU and the memory, we don't know how an architecture is efficient. The only way to know that is to analyze the carbon footprint breakdown, including the main blocks of a chip and how it is used. That will help us to identify opportunities of technology development. I mean, when the breakdown highlights a part of the system which is less efficient compared to the other part. These new technologies will then be used and useful to identify new system architectures. When we do this carbon footprint breakdown, it has to be done with the following concept. Three main functions can be considered in a system. Computing, so the part that creates value by processing the data. New data are generated by an application. Data access, so allowing a remote user to send data to the system or to retrieve the data from the system. That is handled by a network protocol, for example. And the third function, this is the storage. These three functions are operated by different modules and chips. The CPU, network card, SSD, memories, and so on. Each of them can be used for multiple functions. For example, the CPU computes the data, processes a network protocol, and manages a file system. The question behind that, is it efficient in terms of carbon footprint? So, for each function, we will analyze how are used the resources. The resources are the silicon area and the power consumption. These resources can be correctly used or not optimized due to technical limitations. Let's now introduce a proposal to define the system architecture efficiency in terms of carbon footprint. The three first criteria are related to the three main functions. Computing, provided in flops per kilogram of carbon dioxide equivalent. And here it is easy to understand that if we use an accelerator, such as a GPU, then the efficiency will be higher. The storage in terabyte per kilogram of carbon dioxide equivalent. Note that here it does not take into account the storage performance like the IOPS or the latency. And the data access provided in a bandwidth per kilogram of carbon dioxide equivalent. The last one is the most interesting one, since it takes into account the data movement. In a system, there are many data movements between temporary memories. It is just a necessary mechanism because there are physical limitations. But this data movement does not create value directly, such as computing, storage, or the data access. So, if we calculate this ratio, that's a good way to quantify the overall efficiency. How to calculate it? With the Carbon Calculator Studio tool, I have did this carbon footprint breakdown. I have considered that all the memory related parts are for the data movement. For example, at the DIMM level, that includes the DRAM itself, but also the memory controller of the CPU. So here I have estimated the silicon area and the related power consumption of the memory controller in order to estimate the carbon footprint of the data movement related to the memory, but on the CPU side. So for example, in this computational storage benchmark, we can see that the efficiency of the data movement has been multiplied by 2. Now, after this deep analysis of a carbon footprint, let's move on the carbon footprint reduction, because this is the main goal. We can consider 3 main areas with interesting benefits. More efficient function with computing, 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 technologies such as DNA. It is not very fast at this time, but very, very efficient in terms of terabyte per kilogram of carbon dioxide. Data access with the use of SmartNIC, and the efficiency of the data movement as well, since it's not impossible to remove the data movement in the system. And for that, we can use silicon photonics in 3D chips or on the motherboard. The second area is less data movement. By designing more integrated technologies, such as computational storage, as we saw in this presentation, or with processor in memory, where the concept is similar to computational storage, adding computing capabilities in a memory module directly. And the third area is related to the system design. We saw that the scope 3 can be a huge part of the total carbon footprint. So a good way to reduce is to increase the lifetime of a system. For example, do not change all the parts of the system, just do some upgrades and keep the other parts with a modular approach. Or increase the lifetime with a more reliable design, for example, by using an MRAM as a write buffer for SSDs with write-intensive workload. Then, in conclusion, computational storage provides great benefits in terms of carbon footprint reduction, up to about 4x in the example we analyzed. There is a real need to get tools able to provide a very detailed carbon footprint breakdown. This is not for fun. This is just mandatory to build eco-design system in the future. That will also help in identifying new technology development opportunities with eco-friendly features. So technologies or chips with an optimized silicon area, a lower power consumption, and a longer lifetime. In parallel of this hardware point of view, the same approach should be done at the application level in order to analyze the efficiency of all the microservices. Thank you very much for your attention. I hope that now you better understand what is the carbon footprint of a system and how to calculate it and why it is important to do this detailed breakdown. Thank you and goodbye.